In our next installment, we're going to look at a worked example and another conservation of momentum. And we have a boxcar coasting along like so. And we have its mass, and it's coasting along. So we'll draw our boxcar coasting along, and we'll just say this because we don't see any directions. It has a velocity of 4.0 meters per second. It collides and couples. Well, railway cars couple, they join with two identical coupled rail cars. So there are two identical rail cars that are already coupled, moving in the opposite direction at 2.5 meters per second. Aha, so that tells us the velocity is negative. We can make this positive and this negative, and now we have our scenario. These two things are going to collide with each other. The three coupled cars. So what we know afterward is all three of them are stuck together. And they're either moving in that direction or this direction. Now, we want to think about this system comprising the three railway cars. We can consider the system as having a center of mass. This whole system has momentum. That momentum of the system will be conserved, and we're going to come back to that at the end of the calculation. So let's set up our equation. So we have the initial momentum must equal the momentum afterward, and let's call these cars 1, 2, and 3. So we have the momentum of 1 plus the momentum of 2, 3. And afterward, we're going to have the momentum of 1, 2, 3. So that's the mass of 1, velocity of 1, plus the mass of 2, 3, velocity of 2, 3 will equal the m1, 2, 3 times the new velocity. And we're looking for that velocity. That's our unknown. So we can solve. We can write an expression for this, that the velocity afterward is going to be m1 v1 plus m2 3 v2 3 all over m1 2 3. So this is our expression. This will be true of any scenario like this. So our velocity will be the mass of 1, which is 2,000. And wait a minute, the mass of 2 is... so we have 20,000, excuse me. So we have 20,000 V1 plus the mass of 2, 3, which is 40,000 V2, 3, all over 60,000 60,000. So to simplify our math, we could divide every term, we could divide everything on this one side on the left side by 20,000. And so that'll give us 2, and that will give us 3. So we're left with, V equals V1 plus 2V2, 3 all over 3. So V1, which was 4, plus 2 times minus 2.5 all over 3, gives us 4 minus 5 all over 3, giving us a final velocity of minus 1/3 meters per second, or minus 0.33. Now, it's no coincidence that this is 1/3. There are 3 equal masses, 1, 2, 3. And the total momentum that we had is being shared among those 3. Now we can perform our check. Does the momentum before equal the momentum afterward? Well, the momentum before was 20,000 times 4 plus 40,000 times minus 2.5. So we have 80,000 minus 100,000. So that gives us minus 20,000 momentum. That's what we had before. So the momentum of this entire system was minus 20,000 beforehand. The momentum of the entire system must be minus 20,000 afterward. So we can think of this as having this system, and I mentioned this in the beginning of these three-cart system, is having a center of mass. Somewhere in here there's a center of mass. And that center of mass has a negative momentum moving in that direction. Because the momentum of the system beforehand is negative. So after the collision, that momentum vector needs to remain the same. The momentum vector of the system is that green arrow. Afterward, it must stay the same. So after they couple, or no matter what kinds of collisions and bouncing must happen, that momentum arrow must continue to be the same size. That is what's true of this. The momentum of the system remains constant. So we could have, by realizing the momentum initially was negative, know that the velocity would be negative afterward, because it turns out the momentum of this, the two carts, is greater than the momentum of this, than the left railway car. So that's going to dominate the momentum of the entire system, which means the momentum of the system that's dominated was the right, headed to the left. The momentum of the system is left before, it will be left afterward. All right, so the momentum of the system was minus 20,000 before. Let's check it afterward. Well, let's see. Afterward, we have 60,000 times the mass, or times the velocity, which is minus 1/3. Which is minus 20,000. And so the momentum is conserved. And we know for sure the kinetic energy will not be the same afterward as it is before. Because we don't expect that to happen except in purely theoretical situations that don't exist, but also because this is a sticky collision. The velocities involved before, 1/3, are way less than either of the velocities beforehand. Remember, the kinetic energy is dominated by the velocity term. 4 squared, 2.5 squared versus 0.3 squared. In fact, it'll be smaller when you square a decimal number. So we expect that kinetic energy to be far, far less.